Okay, so we've seen transformations, how they affect those 5 stock functions. But I also need to make sure you can do transformations to sort of, just a generic function like this, that you have a graph for, but you don't actually have, it's not one of your stock 5 functions. So on a function that's like this, where you're given its graph, but you're prompted to do some transformations on it, as long as you got the graph, you got everything you need, because transformations are heavily graph-based. So this function g of x that we're referring to right here, it's kind of a zigzag shaped function, probably piecewise, but we don't need to derive the formula for it. Starts over here at the x value -6, goes up at a slope of 1, makes a hard right angle turn, catches the origin as another x-intercept and a y-intercept too, then comes down here to x equals 3, makes another right angle turn, and comes back to the x-axis at +6. So yeah, just sort of a zigzag shape. What I want to do is take this shape and do these 3 transformations to it. So what you want to do is start from a reference version of the original graph, and then apply the transformations to the function g, one at a time. So this first example, we're creating a new function f of x by taking g of x and moving it 1 click to the right and 4 clicks up. So it does help to go ahead and actually plot the original function here. So let me just go ahead and, well, even if you don't plot the original function, plot maybe the corner points that represent the, maybe the intercepts and the turning points on the graph right there. So if I just plot those few points, just those 5, the one at the x-intercept, the turning point here, intercept at the origin, a turning point there, and one there. Since this only involves shifting, I could just take these points, these 5 points one at a time, and do those 2 transformations to them. So I want to take each of these and go 1 right and 4 up. So right and up. So for each of these points, if I go 1 click right and 1, 2, 3, 4 clicks up, 1 point at a time, 1 right, 4 up, 1 right, 4 up. Is the origin point getting shifted, 1 right, 4 up, and then the last point, 1 right, 4 up. Connect these new points with the same zigzag shape you see right there, and you're guaranteed to have the correct graph for the transform function f of x. So after doing those 2 transformations, the function f of x turns g of x into this graph. Okay, so just for, I guess, reference purposes, I'll go ahead and put the original graph in there so you can see how the shifting transformed it. Okay, so transformations you're requested to do here. There are 3 transformations in this one. A negative and a 2. Remember, each of those represent 2 different things. Reflecting about the x-axis, doubling or stretching the y values by a factor of 2, and then after the multiplication of those 2 are done, you shift down by 1. So I do want to definitely reproduce the original graph here, because there's a series of transformations involved with this one. So, and then back down to the origin from the original graph, down here to this corner point, and then back up to the x-axis at 6. So the dotted graph there is my original unchanged graph of g. Okay, so the 2 things I want to do is I want to reflect it and double the y values. So let's do the reflection first. Do that in green. So reflect x-axis, doing that first. So the 3 points that are on the x-axis aren't going to move. This point's going to reflect down here. This point is going to reflect up here. So the reflected graph looks something like this. Now in green, that's the first transformation I did. Okay, now I want to take care of the 2. The 2 causes me to double the y values. So again, I'm referring to the green graph. I've already done one of my transformations. Now I want to double the y values on the green graph, and again, Multiplication is not going to change those 3 x-intercepts, so those points will still stay unchanged. But the point right here, where the y value is -6, or correction, the y value is -3, will double to a -6. And remember, we've already accommodated the minus. Don't multiply by -2. You'll undo your reflection. We did the minus as the reflection. Now we're doing the 2 as the doubling. So double your -3 to a -6 here. Double your +3 y value to a +6 here. And then remember, the x-axis points are still going to stay as is. So this will look something like this when you get that reflection and stretching done. So then, committing to the final graph in red, the last transformation you can do here is to go down by 1 unit. So if I take that purple graph and move those corner points down by 1, this grid's really tight, so it almost looks like it's the same graph, but it technically shouldn't intersect the purple one. You know, labeling your points accurately is a big thing with this, so that way you can know exactly where your final graph should get its plotting. So for reference, the final graph starts over here at the point -6, -1 after doing all the transformations to it, comes down here to the point -3, -7, and then comes back up to the y-axis at 0, -1, and then continues up into the first quadrant at the point 3 for x, 5 for y, and then comes back down here to the point x equals 6, y equals -1. That's what the final graph should look like after doing those transformations. Okay? And one more example. Let me go back to my original graph of G and plot it real quickly so we can do these transformations to it. Okay. Alright, so there's the original zigzaggy shape of G. The 2 transformations done here are a reflection about the y-axis, because that's a negative on the inside. So that is y-axis reflect. And then the final transformation here, since that's a factor of 3 and it's on the inside, it always has the inverse effect. You need to take 1/3 of the original x values. Okay, so let's do the reflection first. A y-axis reflection will take everything about the y-axis, so this point will reflect over to this one, and this one will reflect over there, so they'll essentially stay in the same place. This point will reflect over here. This point reflects about the y-axis over here, so you're just looking at symmetric spacing on either side of the y-axis when you reflect it. So you still get this. That's a reflection, still a rigid transformation. We haven't changed its shape yet, just its orientation. So the green graph is a reflection about the y-axis, and notice same thing as a reflection about the x-axis from the previous one we did. Now I want to take 1/3 of all the x values on the green graph. I'll graph that in red. So again, the easiest points to use are those corner points. So starting here, the x value at this point is -6. 1/3 of -6 shrinks me way down to -2. So I know this point gets morphed or transformed or shrunk to right there. 1/3 of the x value here, this x value is -3. 1/3 there takes you to -1. Okay, so you're considerably shrinking the graph down. It's still a function. It's still there, because you know this green line becomes this red line right here in the final graph, just a little bit steeper because of the shrinking. The origin point is going to stay where it is, because after the reflection and the shrinking, it's still the x value 0, so you're not going to change it. The x value here is +3. 1/3 of 3 is 1. The x value here is 6. 1/3 of 6, staying on the same horizontal line, takes you down to a 2. So connecting those red dots with the same shape as the original graph gives you a much more condensed version, or like a compressed version of the zigzag. It got reflected about y and then shrunk by 1/3 to produce a graph that looks something like this. Okay, so that's, using transformations doesn't necessarily have to always apply to the stock functions that we did first. If you have any functions graph, knowing what these symbols do to the graph allow you to produce a new and very accurate version of the transform graph on graph paper.